to make it as interactive as possible, but I'll try my best to make it attractive and interesting. If you have any questions, you can just ask me. Uh, I'm very well versed using Zooms for my meetings, but this is the first time I'm going on with a Google Meet. So if I'm going to miss out something, just let me know, because I'm unable to see the markings as well as some kind of handshakes or something like that. So if you're able to tell me where it is and if you're going to stop me as I go through, it'll be nice, so I can explain you. So quickly about me, as the other professor to explain you. So I'm Alex Noel. You can just call me Alex. So I work at the institute called Shantou University. So it's in China, southmost part of China. So I'm also a member of the key laboratory of digital signal and image processing. So I mainly work on three different things. One is medical images. How it's applied, applying pattern recognition or deep learning techniques for medical images. The second thing I work on is like natural images. Natural images means things that doesn't require any kind of constrained environments. So you just work on, so take an image on the outside, which has got so much of lightning, brightness, and so many other things. You try to take a photograph from that, and you try to get some information from those images. Say, for example, recognizing text from some kind of from natural images. You call those images as from the wild. You call those things as well. Then I work on signal processing. For example, speedophia detection from ECG signals, EMG signals. So I do work on those areas. And I also work on real-time implementations on hardware, like FPGAs and so on. So today I thought I will take something likewise would be interesting. So this is called as an hybrid. So I'm just going to use my pen. So it's called as a U Net model. Let me change the color of the pen so it's more easier. So we call it as a U Net. So you can see here, this is a model called the U Net model. So this is a part of the CNN. You call it as the convolutional neural network or the deep networks. You call these things. And I'm going to apply this U Net for a very classical problem in medical images. Especially in medical images, you go for two different things. One is diagnosis. So you say whether the person is having cancer or not. That is diagnosis. And another one is looking at the shape of the problem. That comes under the segmentation aspect. So I'm going to use a CNN called the U Net. I'm going to add something called a hybrid, which is my own ideas from our lab. So we call it as an hybrid. And this is already there, the U Net. And I'm going to apply it for a very classical problem called the segmentation. Okay? So the contents of today's presentation, maybe it will be like about an hour. So you just need to listen it, or at least watch the videos, or in case it's up to you, whatever you want to do. So I will just talk about introduction to what you call the computer vision. So what is computer vision? Very short introduction. I think it's been there for ages. So you can just look onto any textbooks or any videos. You can look into what is computer vision. Then I'll go into what is segmentation, types of segmentation. So you got two different types. I will explain these two things. Applications. And probably if you are in this last 10 years, you know what is this word CNN. Probably you should be knowing this word by now. Everywhere people are using the CNN or deep learning, AI. So everywhere you go around, you heard this word. You probably hear this word every now and then. How to detect this, how to detect that, using AIs and other things. So I will give a short introduction about this AI, CNNs. And I will tell you what is the problem with this, especially this CNN with respect to segmentation. What is the problem? And what is supposed to be done with that problem and how people solve that problem. And I'll speak about the architecture called the U Net, some examples, and the last couple of slides, these things. This is our contribution, say maybe from our lab. Say from our lab back in STU. So our lab is called the Shantou University Lab. So I will speak about what did we do to this unit. So how did we change the unit to give us more accuracy, better response? So I will speak about, and finally I'll give you some results of this model when we compare with other different techniques. Okay. Fine. I'm just going to the first slide, computer vision. So let me change the color of this so it's much more easier. Or maybe, okay, I'll change the projector, fine. So computer vision, you can see a centermost part. So it's a very allied field, which means you got something like, you got signal processing, physics, pattern recognition, mathematics, image processing, artificial intelligence. So you can just take in those informations from here and there and here and there. You put them together and you got a different subject or a course called computer vision. So I was searching for a definition and I got this better definition. It's an interdisciplinary field that deals how computers can be used to gain high-level information from signals and videos. That's one definition you can have about computer vision. And if you are from an engineering background, you can say computer vision actually simplifies the task a human visual system do. So it just simplifies a task, or it automates the task which a human visual system does. And from an engineering point, you can call that as well. And for the recent last 10 to 12 years, if you look closely, this has become a big thing. The deep learning coupled with supercomputers, you can just say you got supercomputers at your place. So if you use these two things, there was a very large, rapid advancement in this field of computer vision. Okay, now coming back into how this computer vision started off, what are the applications, what are the challenges they had? So the first challenge all these engineers had was image classification. So what happened is when they trained the model, they called it as a supervised learning. So we call this word, you might have heard about this word, supervised learning, where you try to make the system learn. You tell the system to learn. Okay. So what you do is you got various classes, say dog, cat, car, and so many things, and you try to give it to the system, and the system starts to learn, which means it gets trained and trained and trained. And once you help the system, so you got a system, you push this information into the system and you say, okay, system, this is a dog, this is a cat, this is a car, this is a truck. You tell the system and the system gets trained. So once the system gets trained, all you want the system to do is, okay, and you send a message to this. You call this as a query. This query is unseen image. So you got a system which is a trained system, and inside the untrained system, you send a query, which is an unseen image. And what you expect from the system to tell you is, okay, I send a cat image. You expect the system to tell you it's a cat. So this was a very simple and a very complicated problem in the early stages of computer vision. And people were able to do it very well. So once they finished off this image classification, they moved on to the next bit of task called classification and localization. So in this classification localization, what they did is, they know where the cat, they know this particular image is a cat, but they want to know which part of the image contains the cat. So this word is called localization. Okay, so what you do is you just put a bounding box on top of this and say these regions contain the cat. So use the word, let me use the word regions. So these regions of pixels are the fundamental particles of the image, as we call as pixels. You say these pixels or regions contain the cat. So from the image classification, you went into the next part, which is classification and localization, where you put a bounding box and say those regions are cat regions. Then they moved on to the next step, object detection. So within an image, you got different things. Say we got a van, you got a cycle, bicycle, you got a dog. So you start to put bounding boxes across each of these and say, okay, this particular region belongs to the dog. This particular region belongs to the bicycle, and this particular region belongs to the car or a van or something like that. So as you start doing it, you start from image classification, localization, and object detection. And one thing, if you noticed it, so you should be able to notice one thing in this, all these, generalizations, you should be able to notice one thing. All these things work on regions. Okay? So now people started something which is a coarse grain. Say you started off on you started from a very coarse grain thing, and then you started moving finer and finer and finer, and then you came into something much more better called a segmentation. So segmentation actually works on each pixel. So earlier it was regions. A region contains more, say, many pixels. Let's just say it has got many pixels. Now we move into another one, which is called segmentation, which is you actually work on pixels. So what you do is, instead of classifying a region, you try to classify a pixel. So you say whether this pixel belongs to class A, class B, class C, or something like that. Say for example, let us take this picture with the center over here. Can you see this picture here? So you got human beings dancing here. Some people are dancing. You got the background. You got the ceilings. You got another walls and all the things. So what you do is actually you're classifying each and every pixel according to their corresponding classes. So this was how the computer vision moved on. They started off from a region where you started off just saying, okay, that is a cat, this is a dog. Then localization, object detection, and finally you went into a fine-grained analysis on this, which is called the segmentation. And this segmentation is one of the classical problems in medical images. So if you take any medical images, so you either go for diagnosis, you say whether this person has got problems or not, or you try to get the shape of it to check whether the complexity is okay. So for example, here you can see this is the shape of a problem. This is the problem, and you can see the segmented value of this. So you can see the problem, the segmentation, the problem, the segmentation. So today we will go into this aspect of this aspect of segmentation. Okay. Now segmentation, if you just go deeper into it, you got two different things. One is called the semantic segmentation, and another one is called the instance segmentation. There are two different ways by which you can segment it. So semantic segmentation, if you just look into it, it's just a binary segmentation. It's basically a binary. What you do is you just say, this is a background and this is a foreground. You just say this. That's it. And this is very helpful in medical images, where you want to detect where the problem is. You just want to see the shape of the problem. So in medical images, this is more helpful. But whereas if you look into the semantic instance segmentation, you can see there are balloons here. You try to segment these balloons, and you also say how many instances of these balloons are present in this case. For example, 1, 2, 3, 4, 5, and 6. So you remove them from the background, you segment them, And then you say how many segments of the same classes are available. So this is called instant segmentation. So here I can show you a good comparison here. Okay, I also added multi-class segmentation as well. Okay, we can explain that. So one in this case, normal semantic segmentation, foreground, background. Instant segmentation, you got the foreground, background, you got the foreground, and in this foreground, you tell how many people are there. How many people are there, you also tell that. And then you have the other classical, the multi-class. I think this is a much more difficult one. So this is much more difficult to work around. So you got multiple instances of the people, and you got multiple regions or multiple classifications or multiple labels here. So the complexity increases this way. So you got a lesser complex, less complex, more complex, and as you go through it, you have more and more complex. And this is the state of the art. So this is right now multi-class segmentation. So present scenarios in medical images, we will be just concentrating on the instant segmentation, which is a much more easier way of doing it. And today I'll be explaining you my problem related to the instant, to the semantic segmentation. If you want to learn more about segmentation, there are certain things we need to know. First thing is, you are not expecting to work on a region. There is no region based. You are not working on a region. And you are not putting a bounding box and saying, this particular region belongs to the person. No. You are actually working on each pixel, which means you are actually trying to get a denser prediction. So within this bounding box, where is this object? You are trying to do that. So this is called dense classification. So you're trying to work more on the denser prediction. And something which is a requirement of the segmentation, which I'm making so the red colors are important ones. If you want to note down this, the red colors are important ones. So if you look into the red color here, you expect the output of the segmentation to have the same resolution as the input image. This is one of the requirements. So this is one of the requirements of the segmentation. So the first one is, you are not working on the bounding box, no bounding box. You're actually working on the object within the bounding box, which means you want a denser segmentation. And the third one is, you're looking for the same size as the input image. So these are some of the requirements of the segmentation. Okay, fine. So some of the applications, so as I told you, I'm just working only on the semantic segmentation, where I'm looking for foreground and background. I'm just trying to classify which is foreground and which is background, or maybe I can say, sorry, this is background and this is foreground. I'll put like this, okay. So in this case, you try to find where the problem is. This is the problem. And from the shape of the problem, say you can say, from the shape of the problem, doctors can detect whether you have some kind of a disease or not. For example, I'm working with medical experts in the regions of breast cancer detection. Okay, so let me try this one. So the breast cancer. Okay, suppose you have a very probable shape like this. You call it as a regular shape. If you have such a kind of shape, then probably this is a benign cancer, which means it's not malignant. But suppose you have a very complex contour, and suppose your cancer is, the shape of the cancer is like this. Okay? This is a very complex scenario on the segmentation. and this will probably tell you it is a malignant cancer. So doctors actually take up the shape as one of the main criteria for detection. So the shape plays a vital role. So whether it has got a complex shape or whether it has got a regular shape, you can actually find out from the segmentation. Then probably you can see from the agriculture point of view, you can try to detect the shape of the trees. From the shadows, you can see this is the shadow, and you can try to detect how the shadow looks like from the trees. And you can also use it for, say, for example, autonomous vehicles here. You can try to find out where the objects are moving, and you can segment the objects which are in the front of you. And from there, you can calculate the distance here. And you can use these measures to actually tell you when to stop your car, when to stop the car which the autonomous car is being driven. So you can use those informations to do it. So these are some of the basic applications of semantic segmentations, where you can find them usage in medical images, some kind of agricultures, and so many other things, and also in normal vehicular means. Okay. So let me quickly grasp whatever I told you now. I started off with computer vision task, where I spoke about the image classification, one of the classical problems. Moved on with classification and localization, which is a much more tedious work. Then I went into object detection, so multi-class detection. Segmentations, which is a very fine-grained value, where you try to classify each and every pixel together. Types of segmentation, semantic segmentation, instant segmentation. I gave you an example of each of these, and also told you about the state-of-the-art, the multi-class segmentations, and some important points that you want to take a note if you want to work on segmentation area, and some of the applications. Okay. Now we go into the second part of the topic, which is called the CNN for segmentation. So CNN, as you know, stands for convolutional neural networks, or convolution or convolutional neural network. It depends upon how you use it. They all come under the class of deep learning. So you can say them as a concept of deep learnings. Okay. So this is a very simple architecture, a very classical architecture of your CNN. So you give some images. These are the input images, and these are, you call them as kernels. Kernels are nothing but filter coefficients. So coefficients. So if you're into, say, discrete time systems or not, if you know this LTI system, have you heard about this LTI system? Linear time invariant system. So what happens is, you take x of n, and this is h of n. If you want to find the response of the system, what you do is, y of n is nothing but x of n convolved with h of n. Similarly, here, this h of n is basically the kernels. What you do is, and your x of n is basically the input images here. What you do is, you just do a convolution between these two things, and you get the y of n, which is basically the response of the system. So this response gives you what is called as feature maps. Here you have feature maps, and these feature maps passed into a rectification layer. So what this rectification layer does is, it has got some kind of a shape. So let me tell you one shape. One shape is called like this. So it is 0, this is 1. It's basically a simple threshold mechanism. So any value below 0, you remove it. Any value above 0, you allow it. So that's called a rectification layer. And you got different types of rectification layers. For example, you got a layer which goes like this. You call this as a sigmoid layer, and it has got a much more shape. It's got a much more strong shape, a tan sigmoid or something like that. Okay, you got various layers there. Okay, so all these layers, what they do is their job is to find out the best information that can be passed through. So this is one thing, yeah. So you get out the feature maps from this, and you pass this to a rectification layer, and then you pass it what is called a pooling layer. I'll explain you what it is. So pooling layer is also, a layer which allows only the best features to pass through. So these three layers form the basic of the CNN. So these are the basic layers of the CNN. And what you do is you replicate these layers in serially. So you take these three layers, let me draw it here. A convolutional layer, let me put it as C1. A ReLU layer, let me put it as R1. And then I put the max pooling layer or pooling layer P1. So this is layer number 1. And I copy these layers many times. Okay. So then what happens is I call this as a deep network. So I copy this layer 2, layer 3, layer 4, and I copy these, and what I call this entire network I call this as a deep network. Earlier, if I just used this one, I call this as a shallow network. But whereas when I do multiple instances of these, I call this whole thing as a deep network. And once I do all these, then finally I get some information at this point. Then I put it into a fully connected network. This fully connected network is nothing but your neural network. I don't know whether you are familiar with this. Neural network is something very simple. You got inputs, some neurons are there. So I just need to draw it in the next one. Okay, I'll draw it in the next one. So let me clear this screen for a bit. So yeah, so you got networks of these being drawn again and again, and finally this one goes into what is called as a fully connected network. It is basically a simple neural network. Neural network, what it has got neurons, the input layers, and you got some kind of again some neurons here. So you call this as the hidden layer, and finally you got an output layer. So all you do is you just connect these in certain mechanisms, and finally these ones get connected and you get finally a classification score. So basically this comes at this point here. Okay, so what happens is, let us get back into this CNN. So you've got these three basic layers, and these three basic layers are copied in series and connected to this fully connected layer. And this system is called as a deep network. So let us see the GUI, so how it works around. Okay, you can look at this if you want to have an idea about this. You can just go to this particular GitHub and you can find out how the neural network works, the convolution neural network works here. So, okay, this is the filter coefficients. We call them as the kernels, or in your case, you can call it as h of n. I'm just speaking in a one-dimension scale, okay? So this kernel moves on the image. This is an image. Your x of n just moves around. You can see it just moves around, and as it moves around, you start to get some kind of multiplication values. So you just get some values here. These are basically convolutional values here, and the regions within these convolutional layers. So you can see the blue regions here. These are called as receptive fields. So if you read some papers, you will come across these words, receptive fields, context, and all that stuff. So I'm just going to clear these. So the region within the convolution, the kernel, the region within the region which the kernel sees as it goes over the image, that particular region is called the receptive field. And whenever they both combine together and give you an output, that is the feature map. Okay, so this is what the convolution operation does. And when you run through these convolution operators, you start to get this kind of information. So this is from one of our papers. Okay, what happens is, this is a face, and after doing some convolution, okay, so you can just see the convolution. This is from layer 1. So you can see some kind of feature maps. Feature maps are basically the edges, some kind of contours which show the shape of the person. And as you go deeper and deeper and deeper, you try to get more and more and more information, because more convolutions happening on that and more information gets through it. So the first step, you can just look here, the input images just convolve, and as they convolve with the convolution operators, you tend to get more information, which we call this in image processing terms or AI terms, you call this as the feature maps. So the next step, you have the feature maps. So next step is basically, I missed out one step, which is called the rectification layer. And I explained to you what is rectification. I think you select values above a threshold. That's what rectification layer does. Okay, so I missed out, it doesn't really matter. So you can use different things here. So I'm just skipping that layer and I'm going to the next one, which is called the pooling operation. And people use the word max pooling. If you just go into any kind of deep learning papers or something, you might have heard about this word called max pooling. So what happens is, max pooling is, it retains only the important features. So important features means features which have got the maximum magnitude. You can say that maximum magnitude. So suppose your feature maps, you take a feature map which is like, which has got a 4x4 feature map. In this case, I'm just showing you a 4x4. Okay, it's already there. Okay, let me go here. So what happens is, you take, within this 4x4, you take, say, 2x2 values here. You consider these 2x2 windows. And you try to find out what is the maximum value. So in this case, 1, 2, 4, 6. Okay, the maximum value is 6. So I put it over here. So in the next case, maximum value, what is it? It's 8, I guess. Okay, you move the 8. Okay, so what happens is, in this all cases, I try to find out the maximum values and take only these maximum values and I pass it to the next layer. Okay, so I don't pass the entire feature maps into the next layer. I don't do that. I just don't do that. I go into a max pooling layer where I take only the maximum features. For example, in this case, 4. I just pass the 4. So I just pass only the maximum layer feature maps, which can give me the maximum information about the particular object. I pass only these things into the next layer, or you can just say the fittest features are passed to the next layer. So I do that. And what happens is, when I do it, the 4x4 image becomes 2x2. You can see here. So what happens is, an image which is of size, a bigger size, after going to the max pooling layer, so let us take n cross n. After going to the maximum pooling layer, it becomes n by 2 cross n by 2. Then after it goes to the second layer output, it becomes n by 4 cross n by 4. Then it becomes n by 8. cross n by 8, and so on. So the size of the information starts to get reduced here. Are you able to follow this? This is one of the important things you need to understand. So what happens is the feature maps tend to get reduced, and this is basically because of the max pooling layer, which helps you to find out what is the best feature that is present within that particular convolutions. So that particular convolution layer will give you a feature map. The rectification layer removes of the unnecessary features. The max pooling layer gives you the best feature, which should be passed to the next stage. But while doing these, what happens is you suffer a problem where the size of the image or the size of the feature maps start to get reduced and reduced and reduced. This is a very big problem. So I've taken a simple example here. So 32, 28, 14, 10, 5. So you can see the size of the image gets reduced, but this is the depth. We call this as the depth because the number of convolutions, which means the number of h of n's. So here probably you got 4 h of n's. Here you got 8 h of n's, 16, 32. So what happens is you get more feature maps. See, these h of n's get combined with your input image. You get more feature maps as you pass down these layers, but the size of the feature maps are very smaller. Okay, so that's what I said. For a typical CNN model, the height and the width of the image gradually reduces because of pooling layer, which helps the features to discover more and more information. I will explain you what is this. Okay. So let us take a simple example here. You take a 3 by 3. The first time you see only this region. But the second time, the image gets downsampled, but you have the same convolution here. But the pixels are moved from year to year, which means you see much more information with the same kernel. That's what it calls as a larger receptive field. As the downsampling increases, you see a larger receptive field, which means you tend to learn more. But the size of the image starts to get reduced. Okay, the image size decreases while the number of convolutions increases. And there is a big problem with this normal CNN. We call this as the model understands what is present, but it loses where it is present. And this where information is very important information in the segmentation. So I'll just go back and explain you what I meant by this. Say, take for example, see, this is pixel number 1, 1, 2, 1, 3, 1, 4. Okay, this is in a 4 by 4 vector. So you take up the best pixel and you put it into a different one. Okay, sorry, this is the best pixel here. So let me clear this. So you got a best pixel here. So you put the best feature or the pixel here, you put it into this. So what happens, this particular thing is right now in 2, 2 location. But whereas what happens is, in the new one, this is mapped to 1, 1. So that's what I'm saying here. As the downsampling goes on and on and on, what happens is you tend to get the best value, which tells you what is present in it, but you lose where it is present in the image. Before the downsampling, the 6 was present at 1, 2 or 1, 2, but no. The 6 was present in 2, 2. But after downsampling, it became 1, 1. So obviously there is a huge change in the spatial locations of the informations. And that spatial location is a big important information when you go to the segmentation problem. Okay. So probably you know this person called Gregory Hilton, who is also called as the father of the new AI. So his team developed what is called the AlexNet. So you might have heard about this network called AlexNet. So he was one of the main contributors to the field of artificial neural networks and deep learnings and all the stuff. So he said in one of his papers, the recent papers which uses cluster computing and other stuff. So he said, pooling operation, which has been used in the convolutional neural networks, is a big mistake. So you accepted it's a big mistake. And the fact it works so well for the CNNs, it is a big disaster. And then he said that for the semantic segmentation, we require the where information. We just don't require, so just for object detection, classification, for these problems, the what information is necessary. You just require only what information. But especially for segmentation, which tells you the shape of the object, this where information is one of the biggest responsibilities and one of the biggest important things you require. And to get the where information, we need to upsample it. And almost when people understood this is a problem, and everybody started working as to how to get this where information. We already have what information from the CNN, but how to get the where information. So that's what we are going to see in the next one. What are the methods by which people work to get the where information? So there was quite a lot of research going on to find out how to upsample the feature maps. So we already know pooling layer. So we already know the CNN has got convolution layer, rectification layer, and pooling layer. And all these things are being placed together, layer 1, layer 2, layer 3. Likewise, you place it and you try to get what information. You try to get what is in that image, whether it is a dog, cat, whatever is it. You try to get the what information. And what we understood that because of the pooling layer, we are also losing the where information, which is the pixel location. This is one of the biggest requirements for segmentations. Okay, so people started working on this and they came up with a beautiful algorithm or a beautiful architecture called the U Net. So U Net, as it stands for, it has got a shape like this. It has got a shape which is like this, so that's the reason it calls as a unit. People sometimes use as VNet, or they also call it a VNet, and so, or you also sometimes you can hear the word encoder, decoder architecture. So you also will be able to search these things, all referred to this whatever I'm saying right now, the UNet. So the UNet, VNet, encoder, decoder architecture all come under the bigger class called the UNet. Okay. So UNet was developed by this famous guy called Olaf Rohenberg. Okay. So he works with us University of Duisburg in Germany. So this structure is like this. So you can see the structure is similar to the shape of the U in the alphabet U. That's the reason they call this as the UNet. So it has got two important things in the structure. One, they call it as the encoder structure. You can see this. This is called as an encoder. And the other structure they also have, let me change the color. Yeah. So you've got another structure which we call as the decoder structure here. So the encoder structure is similar to your CNN. Okay, so maybe it just goes. You can just call a contracting path or a forward path. Then you also have something called the decoder structure here, which goes up and up and up. So you can just draw it like this. It goes up. It's called the expanding path or the upsampler. So one thing, so the encoding part gives you the what information. This is similar to the CNN. So basically CNN gives you the what information. And the decoder path is also called as upsampler. It gives you the where information. And there are certain things that we need to know in between. How do they get the upsampling? So for that, what they do is, at every stage, they copy some information from the forward pass to the backward pass. So from this part, they copy some information because there is less information at this stage. So they try to copy it here. All they do is they copy from here each stage. They try to copy it. So these are called as skip connections. So these are terms they use in this, artificial neural networks, or in if you just go to any of these sites called Medium Network, Medium.com. If you just go there, they use these words called skip connections, copy and crop. So all they do is they take features from the encoder layer and they put it along to the decoder layer so that the feature maps get bigger. Okay, so you can see this old structure uses a simple 3x3 convolutions, which means your h of n comma m is 3x3. Okay, so you just have these structures here. So it just goes and goes and goes. So as it goes around to this part, okay, so you get more information. You call this as a what information, and as it expands, you get the where information. And if you see the final output, that's more important than the CNN, the segmentation outputs are of the same size as the input image, which is one of the main requirements. I told you earlier, that's one of the main requirements for segmentation algorithms. It's not just saying which pixel is it. The pixels should be labeled correctly. The final output that comes out should have the same size as the input. That's one of the requirements of segmentation algorithms. Okay, and that is achieved only through these, the upsampling paths. Okay. Now, UNet. So likewise, we saw about segmentation. So now we see some information about the UNet. Okay, first the encoder part. In the encoder part, the size of the image gradually reduces. Okay, the gradually reduces. This is basically because of the max pooling part. We understood why we require it and why the size actually reduces because of the max pooling part, and the depth increase. What I mean by depth is the number of h of n's that you are using. Okay, so you use more and more in h of n, so you get more and more feature maps, which gets more information for it. And this architecture of the encoder is basically the same as the CNN architecture. Okay. Then you have the decoder architecture, which is completely opposite to the encoder. The size of the image gradually increases. This is basically the upsampling part. The depth also decreases. Here the depth increases, here depth decreases. So to get the precise locations, what we do is, how to improve it, we just copy some information from the encoder part and put it onto the decoder part, and we do a couple of convolutions on this. If you look here, we copy it. So some information from here goes up, some information gets added up. You concatenate these two information. It's called concatenation here, which means it's adding up at the end. Sorry, my pen is not working properly. And then this is followed by two convolutions. Okay, you just do two convolutions. So every layer of the decoder takes an input from the lower layer, adds some input from the corresponding encoder layer, concatenates them, then it passes out into two convolutions to give you a better feature map. So likewise, I think this guy has done some research on this and probably tried various iterations, and we came up with this particular architecture, which is a very standardized unit architecture. Okay, so this is what all I was explaining about. The encoder part size reduces, decoder part size increases. At every step of the decoder, you get some information from the encoder and you add it up. From the encoder, you take it to the decoder and you add it up. Then input image goes to the encoder. The height and the width get reduced, but you start to get what information because you focus deeper into the architecture, deeper into the image. Then you have the decoder part. I can gets improved because of the upsampling part. Then you add skip connections to get precise locations. This. Okay. So this is what it is. So you got input image going into the encoder. This gives you what information, and this finally gives you where information. Okay. So this is all about the units. Okay. I think how many? Okay, I've almost spoken like 1 hour. Okay. Okay, fine. Now I'll just go into some of my results, which was done by my student, master student basically. Okay. So you have to check out these things here. So this is an image of breast ultrasound image. You can see there is a problem here. Okay, and doctors have given us the ground truth, which means doctors have told, okay, this particular lesion has got this shape. So you expect your algorithm to classify each pixel in such a way you get this particular shape. So if you work on artificial neural networks and other things, or neural networks, artificial intelligence, neural networks, other stuff, you might have come across this word called supervised learning. Okay. So what the supervised learning is, it tells you, say, suppose you got a black box. Okay, let me go here. So you got a black box. Let this black box called as neural networks. So the supervised learning goes like this. You got a data, huge data you got. Okay, data corresponding ground truth. Okay, so the data says, okay, let me go like this. Okay, dog 1. So let us say we are doing an experiment to classify dogs. So suppose you say dog 1, dog 2, dog 3, dog 4. All these things will be 1, 1, 1, 1, 1. Then you got cats. For cats, it is 0. So cat 1, cat 2, cat 3. So what you do is you show different varieties of dogs. You just don't show only one dog. You show different varieties of dogs. And what you do is you give all of them as 1, 1, 1, which means these are all dogs. And dogs look like these. And because of these looks, the dogs are different from the cats. So what you do is you give a huge data set and you train the neural network. Which means this is called supervised learning, which means you tell the network, this is a dog, this is a cat. Then what happens after training, the network optimizes it, and then you give an unknown sample. You give an unknown sample here, which could be a dog or a cat. The network hasn't seen that, and then you expect the network to say, okay, this unknown a dog here, then you expect the network to say, okay, that is a dog. Next, you expect to send a cat inside the supervised learning as a query. Then you expect the network to say that is a cat. Okay. So likewise, this we are doing it here. So what we did is we spoke with the doctors. We asked the doctors to give us images of the breast. These are images of the breast and how the shape of these breast lesions look like. So the doctors gave us what you call it as mask. So this is basically the background and this is basically the foreground. The doctors would give us this. And what we do is we train about, say, 2,000 images. So likewise, we got different variations of these images. Like 2,000 variations of these images, we gave it and said, this is how it should be looking. This is how it should look. So this is how a dog should look. This is how should a cat should look. So we trained like that. And we trained nearly like 3,000 epochs. Epochs means, it just goes like how many training iterations? Let me call this as iterations. Okay, so if you just look into the mathematics of neural networks, they use the word epochs or generalized word called epochs. It's nothing but iterations. You train them for the 3,000 iterations, and then we tested it. Okay. Now, when we checked it, you should look at these 3 points here. Just look at these. 1, 2, and just give me a second. Just have some water. Yeah, I'll start. Okay. Okay. So this is the convolutional neural network. Convolutions here. The first step has got 16 h of n's. So you got h of n. So let me put h of n comma m 2 dimensions. Let us speak in 2 dimensions. So you got 16 of this. So the input image, something similar to this. So this image is, you can look at the shape, size of it. The size is 512 by 512. Okay. So you take this image, you pass them into 16 different h of n's. Okay. So as you pass through 16 different h of n's, you get 16 different feature maps. You can see here. This is the lesion that looks like with the different filter coefficients, so different values of h of n. So different values of h of n gives you different responses. You can see here. Can you see that? Okay. So what happens is, let us go into the next step, which is called the rectification layer. So what I'm doing here is a simple layer called the ReLU layer. Any value below 0 is removed. Any value above 0 is kept. So you can see how the feature map looks like after, this is the input after convolution, after rectification. You can see we remove unnecessary value. We don't take values below 0. Okay, we can just throw out negative values, fine. Then it goes into the next one, max pooling layer. So what happens is, the image size, note down the image size here, from 512 this becomes 256. But still you can see the features here. What are we looking at? We can still see features. But now it is a reduced image. Okay, so this image again goes into the next layer of your CNN. Again, it gets convolved. So earlier it was 16 h of n's. Now it is 32. We got double. I can't show the entire 32. I'm just showing only 16 here. Randomly, I'm showing you 16. So 4. Yeah, I'm just showing you the 16 of the 32s ones. But still, you can see the what information here. You can see what information coming here. But you lose the where information. Earlier, this position was something like 100. Let us see where it is. So if we look here, this was something like 75 or under somewhere else. But here it has got reduced. The image size has got reduced, right? Can you see it? Earlier it was like 255. Earlier it was like, you can see, this was somewhere here. 125 or something, let us see that location. But after max pooling, this has got reduced here, half of it. Can you see? So you lost the where information completely. But you got the where, what information? The what information is coming out quite well. Because you get more information, more features are coming out, you get more, more information about the lesion you're getting at, but your spatial requirement where it is present, it's just moving off. Now we go into the next bit of the convolution. Now from what do you call 256, this has moved to 120, half of it. Now again you can see here, I think I got 64. I can't show the entire 64. I'm just showing 16 of it. 64 H of n's. So you got only for I think 16 of them. But again, look at, you can still see where this is. But look at the where information. So this is the what information. Where information just changes. Again, we go back still further. Still, I can see the dots, but I'm losing this. Still one more layer. Now we are at here in this case, H of n is 128 different features maps are coming. And finally, my student did this, say he has got 16 here. I think there are 16 here and 16 here. So totally it's 256, I think. And each of these is size of 32 by 32 feature maps. And what happened is you can still see the dots. Can you see it? Now it is more prominent. In fact, it is better than what you see in other cases. So what happens is, as the decoder goes, as the encoder goes, as the image goes through the encoder, the size gets reduced and reduced and reduced. You try to get more information about that, but you lose where it is present in that image. Okay? And now we go into the decoder section. So from 60 to 32, this goes, it gets upsampled to 64 by 64. You can see here, it gets copied from the other layers as well. You can see the size increases, tunable parameters decrease, which means the number of convolutions decreases. Now you again trying to get more resolution, better resolutions, better resolution of the problem. You can see that. And again, still you increase it. Sorry, I'm going back. Okay. And finally, you go to the last stage, which is the 512 case. You can see the image actually come out like this. This image is basically the output of the fully connected layer. Okay, so this image was taken exactly at this point. Okay, let me show you. At this point, my student took it from, I think he has taken at this point of, yeah, he took it at this point. Okay, so you can see, you also have two things you have. You have what information, you also have where information. And this where information is basically from the decoder section of the unit. And this what information is from the encoder section of the unit. Okay, there are two different sections here. Finally, he just does a thresholding based on the analysis. He just does a threshold, finds a threshold point, and then this is the input image he gives in. This is the mask which we are expecting it to come out. The doctors are given this is how it should be corresponding, how the segmentation output should look like, which we call it as a ground truth, which is human annotation. And this is what the computer gave us, the computer output. Okay, so you can see, you can just compare these two things, you get a result out of it. How close is it? Okay, fine. So this is about all about the units. Okay, I told you about the units, all about units here. Okay, how it decreases, how to increase it, the resolution. You could see the images here. And finally, this is all being done by somebody else. So whatever I explained to you till now is basically done by somebody else. And my student wanted to do something more. He came up with a hybrid one. We call this as an hybrid. So, which means you got U Net, you pick some other things from somewhere else. Say, for example, you use attention. I'll tell you what it is. This attention gate is obviously used in natural learning, natural language processing. Then you got something called dilation convolution. So all these things, and you got something called residual networks. So what he did is, he took all these things and he put it into the U Net, and he called this model an hybrid model, and we named this model as RDA U Net. It's called the residual dilated attention gate U Net model. I'll tell you what this model looks like. So this model has got the same shape of the U Net. It has got the same shape, but at the end we have something like this. So we connect it to a tube. Let me call it as a pipe. We connected the two ends to a pipe, and we introduce another pipeline, something here. We don't directly take from the input to the output. We pass them into two different structures. One is called the attention gate. One we called as the attention gate mechanisms, and the other one we called as a dilation convolution mechanism. And we also replace these, the normal convolutions, with what is called as a residual convolution. I will try to go a bit deeper into this if you have time, but if you understand it, it will be better. Okay. The first thing is the improvement is called as the residual network. All these things don't use CNN, they use residual or ResNet. This is another CNN. I will explain you what is the difference between this in the next slide. Then we use another one called the dilation convolution. We don't directly connect it from the encoder to the decoder part. We pass it to a dilation convolution module here. What this module looks like is, so you might know about convolution. Convolution is basically, let me put y of n, h of n, convolved with x of n, sigma, I think k is equal to 1 to n minus 1, h of k into x of n minus k. This is what your convolution formula looks like, and this is the n. So the n will be 1, 2, 3, 4, like this. You move in every particular location. Dilation convolution, what happens is, you move in a different state. So you say 2, 4, 6, 8. So instead of moving one at a time, I move at two at a time. Say first pixel, I take alternate pixels. Then I take alternate 2 pixels, alternate 3 pixels, alternate 4 pixels. So that is basically called as dilation convolution. But I do the same convolution, but I don't take the next value, next pixel. I take the alternate or the relevant ones based on the, say in this case, I interleave 1, I interleave 2, interleave 4, interleave 8, 16, 32. And then what I do is I combine everything and I give it. This is just called as dilation. People say it improves the resolution and improves the information as well. Then we have something called attention gate mechanisms. Okay. What is a gating system? A gating module. Suppose you have an enable system here. Suppose you take a hardware. Okay, let me draw this in a different way. I think I can explain it. Okay. Let us take an AND gate here, a multiplication. So okay, then this goes into another AND gate. And this gives you an output. Okay, so let us say you take A, B. This gives you output C, and you connect this output to the enable pin, where this is called the enable pin, where the user controls it. User controls it. So whenever enable is 1, you get an output. When enable is 0, you get no output. So this kind of system is called as a gating system. Okay, if you look at digital hardware, this is called a gating system. So we use similar mechanism here called the attention gate. So attention gate module, what it does is, whenever it is a foreground, it gives you a 1. Whenever it is a background, it gives you 0. Okay, so we use that kind of technique here, which is basically used in a natural learning process. I think it's used in natural languages, I think so. So whenever there is a text which is of relevant importance, people give 1. The text is of non-importance, people give 0. Okay, similar thing we did here. Whenever the information is relevant, which is basically the foreground, we give more stress to it. Whenever it is a background, it gives 0, which gives lesser importance to it. So this is whenever we take the information from the encoder section and connect it to the decoder section, we pass it to an attention gate module here. It is basically a gating network. Gating, you can just look into digital hardware to understand more about it. Okay, so we introduced these 3 things, and our unit was looking like this. So a residual network, attention gate, dilation convolution. So the residual network, okay, this is the normal convolution. I told you this one, normal convolution. Okay, I just missed out one thing, which is the max pooling. Okay, this is the residual convolution, the ResNet. What happens is, you pass this one here, but you also add it to the input image and get it up. Can you see it? So this one, they use the word called vanishing gradient, solves the problem of vanishing gradient. Okay, vanishing gradient means as the network becomes deeper and deeper, the error which is back propagated becomes constant. So when you train the network starts to saturate. So one can expect like deeper networks give more accuracy. It's not like that. The network has got a constraint. It has got an optimum limit by which you can have so many number of layers. If you increase the layers above a particular thing, the network saturates. And what happens, instead of giving you a better result, it tries to give you a bad result. So that is called as a vanishing gradient problem. And to avoid vanishing gradient problem, what you do is you just add the input to the convolution masks. That's all. And they came up with something called the residual network, which is called the ResNet. Okay. And I told you about the attention gate. This is basically, see the gating mechanisms here. So whenever this is good, you pass this information. You've got a gating information here. You can read about this more in natural language processing. And I also told you about the dilation convolution. You can refer this paper if you want more. It's an open source paper. It's run by my student. And you can see your staff is also here. So you can just look at this paper here. Yeah. So you can look at this work here for more information on this. Yeah, so this is our contributions to this unit. And next thing is we have to prove it, which is better, whether our method is better or not. So we did two different, I think many experiments, I think. Okay, first, yeah. So our proof will be on two bases. One is qualitative and quantitative. Qualitative means looking at it. You look at the image and say, okay, which is better. Then quantitative means some statistical values. Okay. We took up images. So we were in contact with people from Netherlands. We took some images from there, and we used those images to train the network, because you require different images for training and different images for testing. So this is for training purposes and training, and you call this as validation as well. We train the images and we try to validate the network. Then we do testing. So we had some images from our own hospital. So we have some cooperation with the hospitals in Shantou. So we took those images, and we also took some publicly available data. So you can just look at this particular reference if you want to have some more information. So these people have given the data sets. So we took them and we used about 200 images to test our method, okay? And these images are unseen during the training process. And now you can see this, the results. The results are from our RDA U Net. The first one, I'm just showing you the results from the RDA U Net model. I think this one is the ground truth. I think B should be ground truth. I always put B as a ground. Okay, yeah, this is the gold standard. Or you can call this is what doctors gave us, how it should look like doctors gave us. And this is how the computer predicted it, or about how our algorithm, the AI predicted it, how it should be. So you compare these two things and say, okay, is this good? Is this good? So in this case, you can see it is almost good, but the shape you can see it is not that good here. And this is also looks like the shape, but again, it has to go like this. Can you see it? So again, this has missed out some classifications. So in this case, you can note down this point. Some background has been considered as foreground here. Can you see this is a problem? So classification didn't really work out. So what we did is then, and second thing you have to understand these, look at these original images here. This is very important. So you probably may not be able to get those informations and understand how the doctors look like. See, this one is a very complicated structure. See the shape of it. Goes like this, goes like this, goes like this, you know. So this is probably a malignant lesion. And this also probably a malignant, you can see. The shape is quite complex. And doctors take this shape, the contour of it, as one of the criteria for diagnosis. Even this one, say, this one has got some kind of, you know, I don't know whether the student put that word, okay, let me have a look at the paper, okay. So this looks like very like malignant. Whereas take this one, the shape is quite regular, it's more circular. This probably is a benign one. I'm not a doctor, but by profession, I'm not a physician. But when I discussed with other people, they were telling me the shape plays a vital role when you diagnose it. And also the echoes. So these echoes is also very important. Okay, the echoes and how this, so how this one gets into the tissues. So for example, malignant ones disperse themselves into the tissues quite efficiently. And you don't have a proper, so in this case, you don't have proper boundaries. If you look closely, the boundaries are not clearly visible from the ultrasound images. So probably they get dispersed into the tissues. This could be a very classical case of a malignant tumor. Okay. Whereas if you just see this, these ones, you got the boundaries more perfect boundaries, not being dispersed into the tissues. You can actually segment them more efficiently. So these could be like a benign ones. Okay, fine. Now we compared it with other techniques. So we compared like say about 10 to 12 models. We compared it. There are so many different models which are available. So all these are variants of UNet or CNN. Okay, the CNN has got only the encoder path, whereas the UNet has got both encoder and decoder path. Okay, so you can look here. You can just look at those images. So the second one is basically our output. And I think you can just look at the paper. It's much more easier to look at the paper. What are those others 11 ones are? I think it's 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, the other 12 ones you can check. Yeah, what are those? Okay. Finally, yeah, some more images. You can check how well ours is segmented. So this is a very classical case of a malignant. You can see the shape is not very prevalent. A malignant, probably malignant. This is also a malignant. It looks like that. Okay. So these are some of the segmentation outputs we got, and these have been compared with other segmentation techniques as well. Okay. And finally, results. Okay. Something you need to know, and especially with deep learning and machine learning things. This word accuracy has no meaning. The word accuracy, especially in deep learning or any kind of decision systems, has no value, no meaning. Accuracy doesn't have any doesn't provide any information about your system. For deep networks, you require the term called the F-score. Okay, so this tells you. So if you look at the formula for that, I think it's 2 into precision recall by 2 into precision plus recall. You can check that formula. I think it's somewhere close to this. Okay. So to detect this, what you do is you do what is called as the confusion matrix. So you start with the confusion matrix here. What do you mean by the confusion matrix is, you draw a graph here, a table here, and you say, okay, so number of pixels, so you call true positives, false positives, true negatives, false negatives. Okay, so you try to group them into any of these values. For example, true means once doctors say, so let me put doctors say 1, my algorithms say 1, then it becomes true positive. False positives, doctor says 0, my algorithm says 1. That's called false positives. Let me put a different color here to differentiate it much more easier. Okay, put a green color for this. Okay, false positives. Now false negatives. Okay, again a different color for this. Doctor says 1, I say, algorithm says 0. True negative, doctor says 0, the algorithm says 0. So you need to find out this bit, where this is going wrong and how much it is going wrong. So that will tell you the score, which is called the F-score. This is what is important for any decision systems, okay? So if you want to work on a decision system, forget accuracy. Accuracy is basically for measurements. It tells you how close to the original value. That's what accuracy tells you. And it gives you a plus or minus tolerance value. That's where accuracy is used in measurements, not in decision system. You can just say accurate, okay, fine. But if you want to say a system as an industrial system, you need to go for the F-score, okay? And for that, you have to work out the confusion matrix. And let me go back here, yeah. So apart from certain weird ones, so this is area under the curve, okay? You can just look into it. And this is mean IOU. IOU stands for intersection of union, okay? I'll again go back here. Okay. This is doctor's. I'll tell you what is IOU. Doctor has marked it, and my output comes out. Okay, let me draw my output. My output goes correctly like this, but shape goes out somewhere like this. Okay, I take. Okay, so this is the red one is my computer output. Computer output. The blue one is the doctor output. IOU tells you how much this intersect. What is the percentage of intersection? Okay, the percentage of intersection, what the doctor says. If the percentage of intersection is very high, then this is a very good algorithm. So especially you use this IOU for segmentation algorithms. Okay, because doctor gives you one shape and you predict one shape and you find out how much these two shapes are close enough. Your predicted shape is something like this. And if it's very closer to this, then you say, okay, my algorithm is better. Okay, so this is more important. One of the main, criteria. You need to know die-score is almost similar to IOU as well. Yeah. Okay. So this is loss in the sense how close the lower the loss, better the thing. Accuracy, as I told you, it's okay, but not relevant to the digital systems. Especially segmentations. For the segmentations, you require IOU, dice, F-score, and this is called the area under the curve. You want an area under the curve to be an inverted L. So you want to have it like say 1 in this case, so that you have a better response, say 0.9, 0.8, and all are very good responses. Okay, so our output comes somewhere here, the last one. You can say it's quite manageable and better than other algorithms here. Apart from few different things, say for example, this is better, and this one is slightly better. So apart from that, our algorithm, and this one is also slightly better. I don't know which. Okay, dilated unit. Okay, this is also slightly better than that. So apart from that, our algorithm seems to be better than other things. Okay. Okay, so I think I have come to my conclusion slides. I think I almost spent like 1.5 hours. Okay. What did we read from this? Just a small recap. So I started off with a very simple explanation about computer vision. So I started off with what do you call object classification, which is a coarse, C-O-A-R-S-E, coarse, okay, very coarse. Then object classification and localization. Then object identification or object detection. Let me put it like object detection. So these are very coarse ones which work on region-based system. So which means every region has got so many pixels and you classify that entire region. Then I told you about segmentation. I told you it works on pixels, which is basically a fine-grained mechanism. Okay, you work on more granular. The granularity is more fine-grained because you work on pixels. Then we spoke about CNN, I guess. So we went into CNN. Problems with CNN. We found out what are the problems in CNN. I told you about the max pooling problem. I told you how people came across with UNet. Then I explained to you what the UNet does that. For example, the encoder architecture, the decoder architecture, how you upsample this. And finally, I came up with our technique, which is an hybrid architecture, which is the RDA U Net. Okay, I explained these things for you. And I also gave you visual aspects of the algorithm. So you saw the visualizations and also the performance measures. Okay. So I think I have done most of the things. So I told you, so just to remove these things here. You go into segmentation, a unit, what gives you bot as well as bad information required for segmentation. And I also went into the RDA U Net model. I explained to you what it is. So it has got residual networks, dilated networks, attention gate mechanisms, all these gets added up with your unit, and we call this as an hybrid structure. Okay. With this, I conclude my presentation. I think I almost like an hour. And if you have any questions, you can ask me now, or just give me a couple of minutes. I just go through a couple of other slides, and I'll tell you about my research group. So this is Shantou University, okay, from the top. It's in southernmost part of China, very close to a place called Shenzhen. Shenzhen is where you get all your digital products from. And this is my group. So we work with more Indian students, Malaysian students, professors, medical staffs, and other stuff. So I just work here with a couple of the people here. And some of the Indian students come up for internship for us. So we work with them as well. So this work was done with one of the Indian student and one of the Chinese student. We did together. I work on other things like fuzzy and fractal segmentations as well. Classifications on, say, cancer classification on breast ultrasound images. So this is one part of my work as well. This is again, I told you what it's then. This is again, I think the image has gone a bit thing. You got something called AWBUS. It's called the automated whole breast ultrasound images. So we try to do the volumetric analysis of this. And nipple reductions, yeah, it's also done. Okay, fine. With this, I complete it. So if you have any questions, you can ask me. Go ahead. Oh, okay. Should I stop this sharing and take the questions, or which way you want? Ma'am?
Yes, sir. Yeah. Students, if you have any queries.
Rectified linear unit. As I told, after convolution, I may get a positive value, zero value, or a negative value. So this rectified linear unit will neglect all negative values. The function of RDA is to remove all the negative values. Once I do that, my new matrix will be of 20 positive values. Now, from this positive values,
I don't think they have any queries right now.
Okay, ma'am.
I can take average, I can take max.
So on behalf, so I would like to thank you, sir, for sparing time and presenting your work here. Thank you very much.
Which is maximum 27.
Okay, ma'am. Thank you very much. Yeah, thank you guys, yeah, for your listening. Bye-bye.
Nice.
Here I took it as 2 cross 2. I can go for 4 cross 4. I can go for 3 cross 3. So based on my matrix size,